CIT department at New LJ Institute of Engineering and Technology. In last lecture, we have seen the concept of improper integral, and also we have seen types of that, type 1 and type 2, and we have also solved some example. Now today we will see the concept of comparison test, and that is also used to solve the improper integrals. Now the comparison word, right, itself tells you that some comparison is going to be there, and for comparison we will use a function. So obviously we will be having two function, that is suppose fx and phi x. Two functions are there which is bounded in some interval, say a to infinity, and both are integrable. So this is the precondition for that. Two functions, both are bounded in some interval and it should be integrable. Now if phi x is less than or equal to fx for all x greater than or equal to a, then we have to check the convergency of fx. So first case is if integration a to infinity fx dx is convergent, then we can say that integration a to infinity phi x dx is also convergent. That means what? We will be having two functions. We'll check for the fx convergency. If it is convergent, so directly we can say that phi x is also convergent. Now another condition is phi x is greater or equal to fx, right? Then we can say that if integration a to infinity fx dx is divergent, so phi x is also divergent. So this is basically what? Comparison test. Now in that example you will be giving only one function. So you have to assume that function as a phi x. Now from phi x will derive a one function which is which one? Fx, and that function should be in a such a way that either it will be less than or equal to phi x or it will be greater or equal to phi x. So depending upon that condition we'll be having one function, that is fx. Now for fx we'll check the convergency, right? If it will be convergent, so we can say that the phi x is also convergent, and that is for only this condition, phi x is less than or equal to fx. If phi x is greater than or equal to fx, so if this fx is divergent, we can say that phi x is also divergent. So using comparison test we can solve the improper integral. Now before going for the example, there is another convergency test is also there. So first we will see that convergency test, and using both the concept comparison test and convergency test will solve one example. So now we will see the convergency test. So convergency test. Integration a to infinity dx upon x raised to n, and that is for a greater than 0. Now for solving this we'll rewrite it with what? Limit, right? So equal to limit, say example x tends to infinity. So integration a to x. Instead of infinity, we have write what? X. Dx upon x raised to n. So x raised to n can be written as a x raised to minus n. So limit x tends to infinity, integration a to x raised to minus n dx. So the integration of x raised to minus n. So it can be rewrite as limit x tends to infinity, then integration of this, that would be x raised to minus n plus 1, whatever power will be there, will add one value into that upon minus n plus 1. Now we'll also apply this concept, that means upper bound and lower bound. So here it will be what? A, and x is a upper bound. So this will be this. Now we'll rewrite it with the boundary. So limit x tends to infinity, that is minus n plus 1 will be rewrite as 1 minus n. Now x raised to n plus 1, that will be as it is, right? Minus, instead of x, we'll put what? A. So a raised to minus n plus 1. A raised to minus n plus 1. So it will be like this. Now, if we will put directly x equal to infinity here, right? So we will not get an answer. Why? Because here there will be a value what? N. So that answer will be depend upon the value of n. So now we will assume the value of n and will try to solve this example, right? That means what? N. N either can be a greater than 1, less than 1, or n equal to 1. So we'll try to solve it with all these three possibility. First we will take, suppose, case 1, that will be n greater than 1. N greater than 1, here we will be having 1 minus n, right? So 1 minus n. 1 minus n can be what? Less than 0. So what we'll try to do? 1 minus is always a what? Negative. We can say it will be a negative. So what is the possibility of this? This will be the constant, right? A raised to 1 minus n and 1 minus n. Now what is about this? So we'll write it, limit x tends to infinity, x raised to, here it is what? 1 minus n. Now what happened? This 1 minus n is a negative. So for example, assume that it is either minus 1, minus 2, like that, minus. So it can be written as a what? 1 upon x, and here some power will be there. For example, 1. Now if we'll put the value of infinity instead of x, so it will become 1 upon infinity, right? So answer of 1 upon infinity, that is what? 0. So we can say that the value of this term will become a 0, and the remaining is a what? Constant one. So that can be possible with what? We can write that the value of this is minus a raised to n plus 1 upon 1 minus n. We can say that this value is a what? Finite value, right? And if we will get a finite value, as per the previous lecture, this is called a conversion. That means limit x tends to infinity, integration a to x dx upon x raised to n is convergent, right, for which when n is greater than 1. Now the second case is case 2, n is, we can say, a less than 1. So n is less than 1. So obviously the 1 minus n would be what? It will be greater than 0. So obviously the reverse case of this one. So we can say that the integration of a to infinity dx upon x raised to n, the answer will be what? Infinity. And infinity, that means it is divergent. So it is divergent, for which condition n is less than 1. Now case 3, we'll assume n equal to 1. So n equal to 1 will directly put into the main equation, right? So that is limit x tends to infinity, here a to x dx upon x, that means 1 by x dx. Now integration of 1 upon x, that is log x. So it is limit x tends to infinity log x, right? Now this boundary can be rewrite as this a n x. Now again limit x tends to infinity log x minus log a. Now put the value of this x to infinity. So it will become what? Log infinity minus, this is some constant. But log infinity is what? Infinity. So infinity minus some constant value, obviously it will give you the answer what? Infinity. So that is also infinity. So same as this case. If you will get a infinite value, so it is what? Divergent. So if this kind of function is given, that means what? 1 upon x raised to something. So that we have to consider what? N. So from directly the value of n, we can say that this integration is convergent or divergent. How? If n is greater than 1, so that is what? Convergent. And if n is less than 1 or equal to 1, so it is divergent. That means if this type of question will be there, x raised to something, so directly we can say that either it is a divergent or convergent. So this is which? Convergency test. So using comparison test and convergency test, we can say that the integration is divergent or convergent. So let's take one example. Now example is integration 0 to infinity cos x upon 1 plus x square dx. So as per the comparison test, first we'll say that suppose this is our phi x, right? What? Cos x upon 1 plus x square, and we'll find out a fx such that either this phi x is less than or equal to fx or greater than or equal to fx. So suppose fx equal to 1 upon 1 plus x square. Right? We have assumed that fx is equal to 1 upon 1 plus x square. Now, if we'll check the comparison between these two, so we'll get what? Cos x upon 1 plus x square mod is always less than or equal to 1 upon 1 plus x square because of the cos x, because cos x is mod cos x is always less than or equal to 1, and here the denominator of both the things are always what? Same. So obviously if it is less than or equal to 1, so this whole quantity is going to be less than or equal to this function. So we have assumed this is our fx. Now we'll try to find out the convergency of fx. So let's that I equal to integration 0 to infinity and fx dx. So instead of fx, we'll write what? 1 upon 1 plus x square dx. And before that, we'll write what? Limit. So limit x tends to infinity. And instead of infinity, we'll write what? X. Now 1 upon 1 plus x square. Integration of that is tan inverse x. So we will rewrite it integration 0 to x tan inverse x, right? Again we can write it with what? 0 to x will be here. So we'll write 0 to x. Now again we will rewrite limit x tends to infinity tan inverse x minus tan inverse 0, right? So that will become 0. So no need to write that thing, only tan inverse x. Now instead of x, we'll write down what? Infinity, limit concept. So tan inverse infinity. Tan inverse infinity, that will be what? Pi by 2, and that is a finite value. So we can say that it is what? Convergent. So phi x is less than or equal to fx, and fx is what? Convergent. So we can write that by comparison test. By comparison test, we can say that phi x is also convergent. So the main thing is what? Whatever is given, you have to assume it as a what? Phi x, and from that try to derive a fx and then check the convergency. Now another example is, suppose 0 to infinity sin square x upon x square dx. So this is obviously we have to assume what? It is phi x. Now fx. So fx is, suppose 1 upon x square, right? So obviously same as the previous case, sin square x upon x square, that means phi x is always less than or equal to fx. So we'll check the convergency of fx. So we'll write it as a what? Limit x tends to infinity 0 to x and fx dx. Instead of fx, 1 upon x square dx. Now we'll do integration of this one, right? But we have already seen the convergency test. In that, the form is what? Something like 1 upon x raised to n. So same we can say here, right? X raised to 2. So it is like x raised to n. So we can write that from convergency test. Here n equal to 2 and that is greater than 1. Right? So if n greater than 1, we have seen the three cases. N greater than 1, less than 1 and equal to 1. So if n greater than 1, so that is what? Convergent. So our fx is convergent. This is from what? Convergency test. Now, if fx is convergent and this condition is satisfied, so from comparison test, we can say that phi x is also convergent.